1. This is the diagonal. This is super diagonal. This is 0. Is it okay? Correct? This is the way. See, now I am between J 5 or 1J. We can say 5 by 5 matrix. What will be the thing? Lambda, 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 lambda. 1, 0, 0, 0. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 2, 3, 4, 0, 0, 0, 0, lambda. You can see the super diagonal. And this is 0, this is 0. This will be very good example for the Jordan law. This says that for this block, there is a chance, if there is an indication of 1, of course, there is an existence of generalized eigenvector. More precisely, the number of Jordan blocks, please write down, the number of Jordan blocks associated with a given eigenvalue, the number of Jordan blocks associated with a given eigenvalue is equal to the linearly independent eigenvectors. The number of Jordan blocks associated with a given eigenvalue is equal to the linearly independent eigenvector associated with that eigenvalue, and that is the geometric multiplicity of the eigenvalue. The number of Jordan blocks associated with a given eigenvalue is equal to the linearly independent eigenvectors associated with that eigenvalue. That is the geometric multiplicity of the eigenvalue. Okay, I think I have learned quite a lot. So let's look at some of the J matrix, and you can tell me how many independent eigenvectors will be there. If I say my lambda or J is how many? Who is having cell phone? Okay, and I must congratulate you, because you can become the minister in one day. I want to see you like Manmohan Singh, or what is our Prime Minister name? I forgot, you will be knowing. Who is the Prime Minister now? Huh? Can you tell me the name of the Prime Minister? I forgot. What is the name of the Prime Minister? Sir? Modi, your friend only. But I cannot tell Modi, I will tell Mr. Modi. So he will be the next Prime Minister. So I am giving you advance congratulations. Please keep it up. I want to see you. So he is our future Prime Minister. If you have any problem, you can contact him, he will solve your problem. Okay. So this is lambda. How many? Okay. What is your conclusion from it? What's your conclusion from it? How many independent eigen? So now we will be looking at this matrix based on your concept of Jordan law. Just now I gave some definition. Look at the definition very carefully and tell me how many independent eigenvectors will be there from this Jordan matrix. How many Jordan block you can get? 3. How? 1 by 1 matrix, 1 by 1 matrix, 1 by 1 matrix. Why? Because we have lambda 0, 0, lambda 0, 0, 0, lambda. So 1 matrix, 1 matrix, 1 matrix. If it is 1, you cannot construct. Why you are constructing? Adjacent is 0, you have done it. So in this case, your independent eigenvectors are 3 independent eigenvectors. Next matrix I will give. Next matrix is lambda 1, 0, 0, lambda 0, 0, 0, lambda. How many independent eigenvectors? 2. How? Because since it is 1, we have
a matrix here and you have a matrix here. So you have got two Jordan block, first Jordan matrix. So this you can write as J1, J2, where J1 is lambda 1, 0, lambda, and J2 is lambda. Right? And these are the sub matrices. And since number of Jordan block is 2, there are 2 independent eigenvectors and 1 generalized eigenvector. Contact excellent, right? Similarly, I'll give another case. Lambda 0, 0, 0, lambda 1, 0, 0, lambda. Since it is 0, this is one matrix, this is 1, we can construct one matrix. Again, we have got 2 independent eigenvectors and 1 generalized eigenvector. So, you can say for these cases, we have, for these cases, I'll refer this and this, 2 linearly independent eigenvectors and 1 generalized eigenvector. Now I will give you another case where we have only one eigenvector and 2 generalized eigenvectors. That means we will be getting only how many Jordan block? 1. I already gave the answer. So how the J matrix will look like? Now we can see how to construct J matrix. Lambda, then 1, 0, 0, lambda, 1, 0, 0. So this has clearly only one Jordan block, because here you cannot stop. Here also you can stop. So to complete only one Jordan block. So you have 1 eigenvectors and 2 generalized eigenvectors. So this rule is actually valid for other cases. Now, my question is how to prove it. This is like child's play I have done. I have given some statement, you accepted the statement. Now the right time to prove it for this case and this case, especially. Why I will get 1 generalized eigenvector here and why I will get 2 generalized eigenvectors. So what I will do, I will take this matrix and try to prove that. So to prove that J has 2 generalized eigenvectors. To prove that J has 2 generalized eigenvectors. How to prove it? So we have P inverse AP equals to J matrix. Okay. So this gives what? AP equals to PJ. We have done it earlier. This we have already done. How to construct P matrix? So I am assuming that for this case we have got 2 generalized eigenvectors. So that I am assuming. I have to justify. So if I assume I have the 2 generalized eigenvectors, so I have my original eigenvector, say x1, or you can directly say u1, 1, u1, 2, u1n. My first generalized eigenvector q1, 1, q1, 2, q1n. Second generalized eigenvector q1 and qn. This I am assuming. If I assume, then what I have to prove? Some property I have already discussed. What I have to prove? Some proof we have to do. I said it has got 2 generalized eigenvectors. I am saying assuming. If I assume there is a relationship between eigenvector and generalized eigenvector, what is that relationship? Pardon?
A minus lambda u square square.
Yes, a minus lambda I u1 equals to 0. A minus lambda 1 I x1 equals to u1. A minus lambda I x2 equals to x1. So I have to prove in that case a minus lambda I u1 equals to 0. A minus lambda I x1 equals to u1. A minus lambda I x2 equals to x1. If I prove, then I can say, okay, my assumption is correct. So this should come from this inter exercise, right? This should come from inter exercise. Let's look at. Okay. So what is the PG? P matrix is known. Q1, Q1 vector and Q2 vector. J matrix is lambda 1, 0. This J matrix is given, right? 0, lambda 1, 0, 0. J matrix is given. Right? So next step is multiply. Next step is what? If I multiply U11, Q11, Q21 will be with this. What will you get? Pj. What columns you are getting? You will get 3 columns. You can tell me the vector form, or if you want, I can write all the forms. Who will dictate for me? First row, first this thing. Lambda u1 for vector 1 1. Then next lambda u1 2. You will get lambda. Am I correct? Next is u11 plus lambda. Next is u21 plus lambda. Q21 un1 plus lambda. Next is u11 q. Okay, q. q11 plus q21. First we tell us what's it. q12 plus lambda. q22 q1n plus lambda q2n pj. I am giving this relation number b. A relationship is coming from AP that I forgot to do, but we can do it here small. A is what? A matrix is, or A matrix, I will just put A matrix, and P matrix is U1, Q1 and Q2 vector. So it is what? A U1 will be what? You can write A U1, A Q1 and A Q2. Am I correct? AP, you agree with this or not? Yes? Red shirt? Agree? This is my relation number A, this is my relation number B. Both has to be equal because AP equals to PG. If AP equals to PG, this AP, what you got? See, each, when you multiply A with Q1, you get a vector. This vector is nothing but AU. This vector is AQ1. This vector is AQ2. Now, these two matrix actually equal. Then what actually happens? First column has to be equal to the first column. Second column has to be equal to the second column. And third column has to be equal to the third column. So what do you get? So comparing A and B. Comparing A and B. Comparing A and B. Comparing A and B.
Q1 equals to lambda U1. Which gives you A minus, first relationship has been proved. Second relationship is AQ1 equals to lambda Q1. What we get? A minus lambda I Q1 equals Q1. Third relationship is AQ2 equals to Q1 plus lambda Q2. Am I correct? So we have A minus lambda I Q2 equals to Q1. This Q1, Q2 are generalized eigenvectors. That shows that, of course, this structure has one eigenvector and two generalized eigenvectors. So what we have talked about the hypothesis, our hypothesis has been now proved mathematically. First I gave the hypothesis, I told the structure of Jordan block, I gave the hypothesis, okay, this is the rule and this is the proof. So if I have eigenvectors, from the eigenvectors, without having the P inverse AP, I can construct the Jordan matrix. We don't have to do all the time P inverse AP. If we have eigenvalues which are distinct, without doing P inverse AP, we can say my J matrix is nothing but diagonal matrix which are lambda 1, lambda 2, lambda 3. Now, if we have two eigenvectors, so now it gives the situation. I am having symmetric matrix. Eigenvalues are lambda 1, lambda 2, lambda 2. What will be my J? Lambda 1, lambda 0, 0.
Lambda 1, 0, 0.
Lambda 1, 0, 0.
0.
No problem because matrix A is symmetric. Matrix A is non-symmetric. So one eigenvalue is there, one eigenvector is independent, one is dependent. How to construct? Lambda 1, 0, 0. Then 0, 1, lambda 2, 1,
0, 1, 0, 0, lambda.
So without finding the eigenvector, we can construct J matrix. We don't need to find eigenvector because we have shown from this detailed analysis that this kind of structure, one has to be eigenvector, one has to be generalized eigenvector. Okay, so we have played quite a lot on the J matrix, and we have proved it. So similarly, we can. Next we will go for one example. I think that is better. One of the examples actually we'll be doing. Matrix A 2, 1, 0, 2. Non-symmetric matrix. I am giving a non-symmetric matrix. 2, 1, 0, 2. What are the eigenvalues? What are the eigenvalues? Same eigenvalue, 2 only. Problem. Same eigenvalue, 2, 2. What's happening? 2 minus 2, 0. 2 minus 2, U1. Sorry, U1, U2. If you don't want to do this one, you can directly do this. So you have 0, 1. 0, 0, U1, U2, 0, 0. From here you can see that dimension of null space is 1. Okay? Because independent algebraic equation is 1. So it is showing that U1 equal to 0. U2 could be anything. So your independent eigenvector is
0 and 0.
1 plus 1 u. What is 1? Why 1?
One is 0.
U1 is 0. No, just a minute. I should not believe you. I should not believe. If I believe, I will do wrong mathematics here. 0 into u1 plus 0 into 1 into u2. So it shows u2 equals to 0. Am I correct?
1 0.
That's what. See, if I believe you, you will give me wrong results. u1 is the ordinal eigenvector, which is 1 0 from here. u2 could be anything alpha, and I am saying alpha equals to 1. Simplest eigenvector is 1 0. Now, how to find the generalist? And dimension of null space equals to 1. That means it is impossible to find another eigenvector. Impossible, because when you have diagonal matrix, you found that rank was 0. That was easy. Here rank is not 0. Since rank is not 0, how to get rank 0? You have to put 0 here. If you put 0 here, again this matrix will become diagonal matrix or a symmetric matrix. In that case, you are easily getting. See the kind of beauty of mathematics here. See the mathematical beauty here. Once you put 0 here, you get 0 here also. Once you get 0, that matrix will be converted to symmetric matrix. There is no chance you have generalized eigenvector. You must be getting 2 independent orthogonal eigenvectors, and that you are getting. Okay, so that's the beauty of the stuff here. So, how to get generalized eigenvector? A minus lambda I q1 equals to q1. What is that? Which is 0 1 0 0 q1 1 q1 2, which is equals to 1 0. Am I correct? So you are getting 0 into q1 1 plus 1 into q2 1 equals to 1. Am I correct? Yes. And you are having another equation, 0 into q1 1 plus 0 into q2 1 equals to 0. This suggests that q2 1 equals to 1. This suggests that q2 1 equals to 1. And q1 could be anything. So, we can get q1 equals to beta and q2 equals to 1. So, q vector could be beta 1 1. Could be 1 1. You can put beta equals to 1. Okay? So, you got the generalized eigenvector 1 1. You got the generalized eigenvector 1 1. And now we can see this generalized eigenvector and these vectors, they are of course not orthogonal. You cannot talk in terms of basis. Okay? This is the way we can actually construct the generalized eigenvector. Now, what will be my P matrix? My eigenvector is, original eigenvector is 1 0. Another one is 1 1. What is P inverse? Remember that this length is 1, this length is not 1. Okay. What's the answer? What's the answer? P inverse. 1 by 1 will be there? Sure. What will be coming outside? 1 by root 2. 1 0 1 1. Am I correct? Yes or no? Yes? Yes or no? No. He is not agreeing. You are not agreeing. Transpose. P inverse is what? I think you are forgetting everything. That's why you are saying transpose. You are not still agreeing. Do you have a relationship between P inverse and P transpose? Is it correct? Yes or no? Okay, if it is not correct or correct, you can verify P inverse AP should be getting the Jordan law. If it is not, it will have to show up. Or you can directly calculate P inverse from here. If you calculate P inverse from our general principle, are you getting the correct result? The determinant is 1 minus 1, yeah. So what are you getting? You are not getting P inverse? What is the relationship P inverse? To try to find out the P inverse, what I do here, question mark, you go, it is possible to find out P inverse from here. If you don't have any formula, you can directly find P inverse. You put P inverse AP, you can directly find P inverse from here. If you are in doubt, you can check it out. And P inverse AP is the Jordan matrix. What Jordan matrix you be expecting here? For this case, what Jordan matrix you be expecting here? Both eigenvectors are same. It has to be like this. One independent eigenvector and one generalized eigenvector. Okay. So your Jordan block should be here. 2. It has to be there. No other way. 2, 1, 0, 2. Okay. So you can see that your original matrix itself is a Jordan matrix, right? Here A equals to J. Am I correct? The original matrix is a Jordan matrix. So that's one of the classic, beautiful example I have drawn here. So we have done the non-symmetric, symmetric matrices, and let's look at much of this. Polynomial of A. Polynomial of A means we say x polynomial. What is that? A0 plus A1x plus A2x square plus AA to the power x. If I say f of A, which is, what should I write? F of A. This you know. We have seen in the school level. Polynomial of x equals to A0 plus A1x plus A2x square plus A2x to the power. What should I write for f of A? F of A will be A0, A0, I, yes, plus A1, A matrix, plus A2, or you can say square, AN. That means you have to multiply A into A. Next will be A square into A. Next will be, and then up to that you get A to the power n minus 1. Then if you multiply with A, you will get A. That is the way this entire series will be done. Okay, this is the way the entire series will be done, and so in that case you can actually evaluate any of the stuff. So same way, when we do the e to the power t, what is that? Which is I plus ta plus t square by 2 factorial plus it is a square and then infinite series, because we know the polynomial of x. Okay, since polynomial of x is replaced by a, similarly e to the power tx will be replaced by 2 power t. That was the argument. Okay, so this part I wanted to mention. I just seeing that what are the things we can actually conclude from this entire analysis. Now we have dx equals to ax dx equals to x, and from here we get dy dt equals to lambda y. Okay, so what is the y solution? E to the power, if I give the initial condition x t equals to t0, x0 vector, what will be that y t equals to t0? y0 vector. So can you express the solution in terms of y0 vector? We have done already in the class. I am just quickly revising what we have done. This is already done. It was done what? E to the power lambda t into c vector. This is a matrix. Why it is matrix? You can see that. This is matrix, this is matrix, this is matrix, so this has to be matrix. This is confirmed from here. This is matrix, so this is matrix, and this n by n matrix, it has to be n by 1 because it is n by 2. So how to evaluate C from initial condition? That means if I put t equals to 0 here, what will happen? It is arranged in a matrix. What will actually happen? T tending to 0, something will be
will be there. So it will be all 0. That means all the entries T will be there, and T0 means all these entries will go. Only one thing is remaining. So what will you get? So T equals to, so this means this I, right? So at T equals to 0, at T equals to 0, why it will be I T equal to 0 into C vector, am I correct? Because it's I only remains, other things all get 0. Okay? Because if you see what is TA, it will be T into all the elements. Everywhere T will be there. And if you put T equal to 0, it's a 0 matrix only. Very simple. Nothing extra can be drawn. And then what actually happens? Why T0 is given, which is Y0. You can put T0 equal to 0. Initial condition. So it is Y0 equals to I into C, and C vector is nothing but Y0 vector. So you can get Y vector is nothing but e to the power lambda T into Y0 vector. Okay? I am giving you maximum number of steps. This many steps I have not given last year in your senior batch. So this is the final solution, and if you want to get solution in terms of x, how to get the solution in terms of x? Y equals to what? P inverse x, or if you put P both sides, what will you get? X. We have done in the class last, I think 2-3 lectures back. If you multiply by P, you will get x, and you get x equals to, if you call lambda T into P into Y0. How to get Y0 from here? X0 is given. So if you how to get Y0 from here? This is not known. How to know? How to be known? Y0? This is only known. See, any problem, I am giving only this much. I am not giving this. How to get Y0? How to get Y0? How to any answer? Do not please murmur. Just don't pass. You know the answer, give me the answer. I am giving only, this is the problem statement. I am asking how to get Y0 vector. Okay, because we know Y equals to P inverse X. So if you put P inverse here, both the sides multiply, you will get Y vector at T0, which is equal to P0. It is multiplied by P inverse. Okay? So this Y0 is known. So now when you get this solution, if I want X vector, you will multiply by P, right? So you get X vector, if the P, if the, so X vector is nothing but, X vector is nothing but P e to the power lambda T Y0 vector. That's the final solution. So that's the final solution. Okay? So it is given, it is possible to multiply by P inverse to get Y0 vector. Finally, you get Y solution. You multiply by P to here to get X, then to get P e to the power lambda T Y0. Right? So now the P inverse AP, there are a lot of proofs actually there. If Ax equals to if I have P inverse AP equals to P, if Ax equals to lambda x, how to prove that B has the same eigenvalue but different eigenvectors? So many things actually coming. We have learned so many things. A matrix is eigenvalue lambda, X are the eigenvectors. How to prove that B matrix will have the same eigenvalue but different eigenvectors? How to start? What to prove? To prove B, Y. That means B matrix has same eigenvalue, different eigenvector. How to prove it? How to prove it? How to prove it? So for everything is okay? Yes or no? This is y, right? P inverse x. And then what will you get? P multiplied by P inverse, right? What will you get? P inverse AP, which is By. P multiplied by P inverse, you will get By. And if you P multiply the P inverse, you will get, since lambda is scalar quantity, you can write P inverse P. And any matrix, the inverse will be identity matrix. It will be I. If you multiply the vector, you get the same vector. You will get lambda. What does that? So with that, you can actually see that if P inverse AP equals to P inverse AP equals to B, you can actually see that By equals to lambda. Right? Formula is clear? Yes or no? Formula is clear. So P inverse AP equals to B, and this relationship is valid if Ax equals to lambda x. For B, it is By equals to lambda y. Okay. I think we'll stop here for today. Next class will be. Okay, another proof. I think I can. You have the time there?
Yes, sir.
Okay.
14 minutes.
Huh?
14 minutes is there.
Okay, another 5 minutes.
14 minutes, sir.
14 minutes.
30.
Okay, fine. So next, I think one or two proofs I can actually do it before I leave, because next class will be on Tuesday. Monday I'm not taking the class. So you are free up to Monday. Next class will be Tuesday. So let's look at another problem. If a matrix A, please write down. If a matrix A has n linearly independent eigenvectors, if a matrix A has n linearly independent eigenvectors, now we are actually having different kind of rule. I am not saying there are orthogonal eigenvectors. If a matrix A has n linearly independent eigenvectors, then P inverse AP equals to lambda. How to do it? We have proved already. How to prove if I ask? We have already proved it because P matrix will construct in terms of eigenvectors, and we can actually prove that AP equals to P lambda. Okay, if you can prove AP equals to P lambda, see if you can prove that way, then in that case we can actually take the inverse. If you take P inverse here, P inverse AP, then P inverse P will be I, and you get P inverse AP equals to lambda. So this kind of proof always you can do by AP equals to P lambda. I am just repeating whatever we have done. Now another interesting thing, P inverse A to the power n, P will be what? Or we can also write this way, P inverse AP equals to J. More theorized, Jordan law. You can also write this as A equals to P. See, what I am trying to say here, you have to find out A to the power n, right? In this e to the power PS series, you have to find out a square A. Now, I will show you how this will be useful to find a square a cube. Otherwise, big matrix you have to go on multiply. For example, I will say evaluate to the power t. I give a matrix. For evaluating into the power t, you need I. You need t into a matrix. You need t square by 2 factorial into a square matrix. You need t cube by 3 factorial a cube matrix. You need t to the power 4 factorial a4 matrix. How to evaluate those a square a cube a to the power 4 easily? I will show you the magic here. A square will be what? P, J, P inverse, P, J, P inverse. Am I correct? Yes. P inverse P equals 1. Right? So it is P, J, P inverse. So
So it is P J square P inverse. So a to the power n will be P J to the power n P inverse. J matrix is very easy. For example, if you have J matrix 1 0 0 0 2 0 0 0 3, what will be J to the power n? 1 to the power n 0 0 0 to the power n 0 0 0 3 to the power n. So if the eigenvectors are known, then if you do this and you get the A square equal. So now you can see that this P matrix is so powerful. Using this P matrix and J matrix, you can get the A square equal A to the power 4 so easily. So those things you can do it. Those things you can do so easily. Okay. So one question can come in the exam. Evaluate to the power P. Okay. I'll give a matrix. Okay. I'll give a matrix. What matrix you want? 1 2 3 0 1 2 0 0 2. What are the eigenvalues? 1 1 2, right? Okay, this is the eigenvalues. Find out into what T. Find out into what T. Okay, so you can see we are having on J1 eigenvector also for this case. So next Monday, maybe who can volunteer to do the into what T by this method? Can you volunteer? Next week is not Monday. You have enough time. So I am asking to evaluate E to the power T by this method. So what you have to find? Already you know I. T is T you have to multiply with A matrix. A square matrix. Even the Jordan block and all those things. With that, I want you to find out E to the power T. So if one has to find out E to the power T, this is the classic example where you can find A square equal so easily. Because you remember that if you find A square equal from here directly, it is very difficult. I can't be imagining, I can do mistake. A square equal, if you want to find again multiply with it, you get A square. Again A square matrix multiply with A cube. Your mind will go, will curse me. What sort of problem here? What problem Sir has given? But if you do this, it's a fun, it's a game. So I want you to play the game. Of course, I am giving you the chart. Anyone if you can give, I will give the bonus point. But what is it? I forgot your name. Amit. So Amit can volunteer for that. Lastly, how much minutes do we have?
Sir, 7 minutes.
7 minutes. Okay. Some more fun actually you can have. Next we are having Calais Hamilton theorem. Next we are having Calais Hamilton theorem. F of A0 A to the power n, or I just put A0 I, A1 A2 A square and AN A to the power n. That means what I am asking, evaluate 5A square plus 3A plus 7 or 5 to the power 2. Will you do like this? How to approach with this method? I want answer. Pardon? Characteristic equation or will not work. Don't use it on school level mathematics. What we have done just now with this technique. Characteristic equation on school level. I want the answer 5A2 plus 3A plus 7. How to evaluate? This is a matrix algebra, you can say. How to evaluate? A0I, A1, P, what you got? PJ P inverse. A1 into Pj P inverse, A2 P J square P inverse plus dot P J to the power n P inverse. Then what can you write? You can take P common, A0 I. Why I can write like this? You can also write P inverse here. Okay? So that means P inverse equals to I. Still you are okay. Next is A1. Because P is already there, P inverse is already there. Next is AN J to the power n. So what you got? P matrix F of J P inverse. Beautiful. F of A is nothing but P matrix F of J P inverse. Okay. What is your polynomial? 5AQ plus 3A plus 2. What will you get finally? If you have 5AQ plus 3A plus 2, what should you get? P of 5 JQ PJ. Excellent, magic. So you can see that how this powerful JJ matrix is and P. With this, anything. So this is another question I can ask in the exam. I'll give some polynomial. You can get the answer like this very quickly. You can even what that if you want to do by direct doing, you do a lot of mistakes. You multiply S square, A, all those things. But here, if you know P and P inverse, this J is very easy to do. Once you do it, so your job is done, you can actually get the answer. So you have done it, right? How many minutes? 2 minutes, okay. I can give the grace of 2 minutes. So next class we'll be doing more such magics. Okay, thanks for kind attention. So next class will be on Tuesday. Attendance record.